let's make a start. It is my great pleasure to introduce our colloquium speaker for tonight, Professor Matthew Inglis. And Matthew has a role as a Professor of Mathematical Cognition at the Mathematical Education Center, which is situated in the Department of Mathematical Sciences at Loughborough University in UK. Despite his very young age, Matthew has made an important contribution to the field already and is well recognized internationally. He currently serves on the editorial boards of 3 journals, namely Educational Studies in Mathematics, Research in Mathematics Education, and the International Journal of Research in Undergraduate Mathematics Education. All 3 journals are considered to be top journals in the field. His achievements have been recognized by many awards, including the Research Fellowship from the Royal Society Worshipful Company of Actuaries for the duration of 5 years. Also, in 2014, he was awarded the Annie and John Selden Prize by the Mathematics Association of America. And in 2017, he was named the Times Higher Education Outstanding Research Supervisor of the Year. Matthew's research accomplishments are many and generally regarded by the research community as being of exceptionally high quality. As of today, Matthew is an author of 80 peer-reviewed publications, 80 exactly, unless I miscounted, 5 book chapters, and 3 remarkable books. We are very pleased to have Matthew here. This is Matthew's first time in New Zealand, and actually, in fact, first time in the Southern Hemisphere. And I have some evidence to say that he's definitely learned something new already. He's learned a new word. It's jandals. And at first, he even struggled to pronounce it correctly. It took him a few times. And I think he was a little bit skeptical about its explanatory power as compared to British flip-flops. But I have to report, after being here for 3.5 weeks, he is now a proud owner of a new pair of Kiwi jandals and is determined to make this term trendy in UK. So we wish them best of luck in this endeavor. And at this time, please join me in welcoming Matthew Inglis.
Thank you very much, Andy. Thank you to everyone. I've had a really lovely time in Auckland so far. You're a very friendly department, and I've thoroughly enjoyed my time here. It's really quite sad I've only got a few days left. But let me tell you a bit about what I'm going to talk to you about today. So my plan is to tell you a bit about a sequence of research some of my colleagues and I have been doing over the last, I don't know, 10 years or so, I suppose, about trying to understand how students read mathematics and how we can help them to improve the way they read. So why we care about this? Well, I'm sure everyone in the room will agree that reading mathematics is actually really important. When you think of the proportion of time students spend learning mathematics from reading, be that in textbooks, through materials we put on our VLEs or equivalent, or even in old-fashioned traditional blackboard writing or in a lecture, a large proportion of learning in undergraduate mathematics takes place by reading. And we know that reading proofs in particular is pretty hard for students. We know that there's a sequence of research now that shows quite convincingly, I think, that students really find difficult how to engage with written proofs. So, here's my plan. I'm going to try and get through 5 studies today, which sort of were the natural sequence that this work took place in. So I'm going to start off by motivating this with a study on what we called e-proofs, which kind of motivated the rest of the work. So, this is my colleague Lara. She was very worried about how students in her analysis class struggled to understand proofs and struggled to engage with written proofs. So she had this good idea. This was her basic idea. She said that understanding proofs from lectures might be quite difficult for a variety of reasons. So if you think about what's required to understand a proof as a lecturer is writing it on the OHP or the Blackboard or whatever, well actually you need to do quite a lot of stuff. You need to rapidly remember basic knowledge. So you need to remember definitions, you need to remember all sorts of things. You need to bring that to mind at the right time. You need to recognise and check or validate logical deductions as they're done by the lecturer. And you also need to recognise some kind of large-scale argumentative structure. So whether it's a direct proof, proof by contradiction, and all that kind of stuff, you need to work at the large scale and at the local scale and record all of this stuff at the same time. So that's going to be quite hard. One issue in particular with Blackboard lectures is it's actually quite hard to direct students' attention precisely. If you're sort of waving around your hands. And another interesting issue is when people do studies of how mathematics lecturers teach, what you find is lecturers spend a lot of time, often at least, the verbal explanations lecturers give tend not to make it into students' notes. So often you find that when students are making lecture notes, they only write down what's written up on the board or on the OHP. And this is a problem because quite often more of the explanatory work is done by lecturers verbally, so that kind of gets lost. So there's all sorts of reasons why understanding proofs in lectures is going to be difficult. So she tried to address these issues with what she called e-proofs. And I will just give you a little demonstration of that now. So this is the kind of resource she designed. It's a proof of this theorem. And here's the proof, and you can see it's like a normal proof, except bits of it are greyed out, and it's got some audio.
From the theorem premise, we know that n is composite. Therefore, n can be expressed as the product of two integers. We assume that n is equal to ab, where a and b are two integers greater than 1 and less than n, with b equal to or greater than a.
Okay, so that's the first step, and you can see we can scroll through the proof like this, and bits and highlights.
In this line, we use the previous line to conclude that since a is an integer and greater than 1, a has a prime factor, say p.
And you can see how it would work, right? So the idea here is that the explanations are saved for students to look at after lectures. It directs their attention very precisely, and the idea is this is going to be much really helpful for students to engage with proofs. Okay, so she did this and everyone was very happy, and indeed students loved these, they absolutely loved them. So we did one of the sort of standard student satisfaction surveys with this kind of statement, and we asked people to rate these statements on a 0 to 4 scale in the kind of way that I'm sure you're all familiar with. And we got uniformly positive responses. So out of a possible 32, the mean was 25.5 with a really tight confidence interval. So it was very, very popular with students. And then we also did various focus groups and interviews and so on. Students absolutely loved these things. Our colleagues loved them as well. So many lecturers said to Lara, look, I would like to be able to design my own versions of these in my own course. So she said, oh, well, okay, we need to develop some kind of computer program that would allow that to happen quite easily. And these people used to have funding schemes for this sort of thing. These are sort of e-learning experts in the UK. So Lara applied for a grant from them, which was reviewed in a normal way, plus an interview actually, so it was quite a robust review process. And they gave the university a £80,000 grant, which is $160,000, to develop more of these and a mechanism for producing, for lecturers to produce their own. So we had all this standard evidence that e-proofs were effective. So we had some qualitative feedback from students, we had some quantitative feedback from students, we had all these peer observations, and we had expert peer review. Now, unfortunately, all of this turned out to be wrong. So we did this robust experimental evaluation of these things, and they actually turned out to hurt students' learning. So, let me tell you what we did. So this was my PhD student, Shamali, and she did a whole thesis on this, but this is the first version of her, one of the early studies. She essentially did a simple experiment where she randomly allocated students to either learn a proof from one of those e-proofs I've just shown you, or what we're calling a textbook proof, which is a bit misleading. That was essentially just exactly the same display on a computer, but without any animation or audio or anything of that sort. So exactly the same display with all the interactivity stripped out. And we gave them some time to study the proof, and then we gave them a comprehension test designed to evaluate how much they'd learned. So even though I'm calling that a textbook, it's not really a literal textbook. Importantly, we also gave them a delayed post-test. So we asked them to do the same comprehension test 2 weeks later. Okay. So what do we find? So the first thing to say is you may be wondering how on earth you do this. And indeed, measuring proof comprehension is a non-trivial task. So there's some really nice work done at Rutgers which tries to come up with a framework for how to do this. And they have various different dimensions of questions you might ask to assess whether someone understands a proof. So for example, one thing you can do is ask them to apply the steps of the proof to a particular example, or transfer the proof to a slightly different context, or, and so on. So that, I'm not going to justify how we did that, you're just going to have to take it as read that you can do that, and we did. Okay, so what did we find? So recall we have 2 tests, an immediate comprehension test and a delayed test. So this was very disappointing. So on the immediate test, we found no difference between the 2 groups. So the e-proof group and the textbook group learned about the same amount. And that was disappointing, but it gets worse. So as you would expect, people forget things, learning degrades over time. So the textbook group dropped off a little bit, but the e-proof group dropped off a lot. And indeed, when you do the statistics, you find that interaction is significant. And what that means is the difference between there and there is smaller, significantly smaller than the difference between there and there. Okay, so this apparently helpful resource that everyone loved was actually hurting our students' learning in the sense it led to lower long-term learning. Now I think there's all sorts of interesting things you can say about this. One thing to say is don't trust standard measures of educational effectiveness we use in higher education. So at least if you're like my university, this is essentially all we do to assess whether our teaching is any good. And you know, if you know the educational research literature, it won't come as a total surprise to you that these are not reliable measures of educational quality, as defined by learning outcomes. So all of those pointed in the same direction. But actually, when we measured student learning, all of those methods were misleading. So we kind of thought, oh, this is disappointing. Our best efforts to improve student reading have gone horribly wrong. Let's go right back to the beginning and start from scratch, and think about how experts and novices read and how they differ. So that was our attempt to sort of use intuition to improve student reading. So we thought, okay, we've got to do some proper research and do it that way instead. So this was the question we asked ourselves in the next study. How do experts and novices read proofs, and how do they differ? So hopefully, if we can work out how they differ, that will give us a sense of the kind of things we might be able to intervene in to help students develop skills in this area. So, for this study, we used a validation paradigm. So when I say validation, what I mean is the activity of reading a proof with the aim of working out whether it's valid or not. So you know, I give you a proof, and you say to me, valid or invalid. And this has been used by other people. So Selden and Selden found that their students, who I think were from Tennessee, don't perform at above chance levels. So they may as well have been guessing whether a proof was valid or not. They also found that their students seem to concentrate on what they call surface features, such as algebraic manipulation. But they raised some concerns about their methods, rightly so, I think. So they said, actually, this is a really hard thing to study, especially with interviews. So they said, a validation is often much longer and more complex than a written proof. It may be difficult to observe because not all of it is conscious. Moreover, even its conscious part may be conducted silently using inner speech and vision. So there's this idea that when you're reading a proof, you're doing all sorts of things that you may not be aware of, and so it's quite hard to work out what those things are. Simply asking you may cause problems because it may affect what you're doing, at least in the extent to you're asking someone to do an extra hard task, both do what you're doing and report on it. So what we did to get around these problems is we recorded mathematicians and students' eye movements as they read proofs and didn't ask them to speak aloud at all. So, if you're not familiar with eye movements, then it's quite simple actually. Essentially, there's only two important eye movements when you're viewing static images. Things get a little bit more complicated when things start moving. Happily, proofs don't move. So eye movements, basically, there's only two sorts you need to care about. One is fixations, which are short stops, where information is processed, and another is a very, very rapid movement to a new location, which is called a saccade. And happily, during saccades, no one can process, information can't be processed. And you can test this by sort of flashing up stuff when people are making saccades and they can't see them. So all you need to do is focus on people's fixations, and this whole approach relies on what Justin Carpenter called the eye-mind hypothesis, which is the claim that there's this close correlation between eye position and visual attention position. So essentially, in general, there's a correlation between what you're thinking about and what you're looking at. Now, of course, this is not 100% correlation, and it's very easy to create counterexamples by looking at people and thinking about something else. But Justin Carpenter showed that in general, and especially when doing something cognitively demanding, there's quite a close relationship between eye position and attention. Another nice thing about eye movements is there's a lot of research that shows that longer individual fixations are associated with deeper processing. So if you give someone a static image, and if you compare different parts of that static image, if you find that fixations are systematically longer on one part than on another part, that tells you something along the lines of the part with the longer fixations is more demanding to process. And that's kind of a useful fact about eye movements, especially in educational research. Okay, so here's an example. So this is a bit of standard English, which in fact was the instructions of our experiment. And this point here is a fixation. And I'm just going to show you what eye movements look like when reading normal English. And now remember this, because I'll ask you to compare it with what it looks like when reading mathematics later. So you can see that eye movements are quite jerky, but when reading standard English, you tend to make fairly systematic progress through the text with a few back saccades, but basically you sort of go along in the kind of way you would imagine. And that's a very standard reading pattern for English text. Okay, so what do? Well, we simply got some mathematicians and some first-year undergraduates to read 6 proofs whilst on an eye tracker. And if you're not familiar with screen-based eye trackers, they essentially just look like computers but with a few hidden cameras which track your pupils. And the task was to read each proof and decide whether it was valid or invalid. Now, several questions here. So firstly, is it the case that students focus on different parts of the proof? In particular, do they focus more on what Selva and Selva call surface features than mathematicians? So here's one of the proofs we use. So this is a proof that there are infinitely many primes that can be written as 4k plus 1, where k is some kind of integer, this proof is invalid. So what did the students look at? So this is a heat map showing their attention location. And the darker the colour there, the more students attended to. You can see the bits they really attended to are in fact all, largely, they've got some kind of symbolism. Not entirely, but largely. And if you compare that to where mathematicians attended, you can see it's really quite different. So they spent a lot more time thinking about this slide, which in fact has the key step of proof in it, and a bit less time worrying about the notation elsewhere. Okay, so that's a nice colourful picture, but you can do that analysis rigorously by calculating each individual's dwell time on formulae and non-formulae, which you can operationalise using LaTeX math mode. So anything within dollar signs, you can think of as being formulae. And this is what you find. So the mathematicians did indeed. So the other thing I should emphasise again is these people were first-year undergraduates, and these people were all mathematicians. So the proofs were really very simple, because they had to be for the first-year undergraduates to be able to engage with them. But nevertheless, mathematicians did seriously engage with this class, and indeed had a longer overall dwell times on the proof. But they looked at different things, right? So the mathematicians spent proportionately more time looking at the formulae compared to the non-formulae compared to the formulae, and the undergraduates were the other way around. And again, when you do the stats, everything that looks like it should be significant there was. So what's going on here? Why are students spending more time looking at formulae? So one explanation is maybe undergraduates just find processing algebra really hard, so they just devote more time to do that. And there is some evidence in our data for that being part of the explanation. So you'll recall I said that the mean fixation duration is a measure of cognitive processing difficulty. And indeed, undergraduates had longer mean fixation durations with our mathematicians on formulae. But actually that can't be the whole story, because if I go back to the graph, you can see that actually they spent the same amount of time on formulae. What's going on there is mathematicians cared a lot more about text than the students. So one way of thinking about these data is maybe what's going on here is undergraduates aren't attending to the logical relationships of the arguments, which often, and in our case, in these proofs, were contained in the text rather than the formulae. So how could we investigate that more precisely? What we did, so that's an interim conclusion. Students don't seem to focus as much on written text proportionately as mathematicians. So another question we were interested in is, so given that they don't focus on the text, are they looking at things in different orders? Now the reason we were interested in this was there was some talk when we were doing this, around the time we were doing this study, that a really effective way of reading proofs was to to do some kind of skim read and then go and do it carefully line by line. We were interested in whether that seemed to be the case, whether mathematicians did that, and whether students did that. So what we did to investigate this question was we looked at all saccades, counted every, threw away saccades that were not, didn't start and end in the proof. So obviously a lot of the time, not a lot, but some of the time, you're just looking at issues or whatever, or blinking, or it's quite noisy data, line movement data. So we threw out everything that wasn't starting and ending in the proof. We counted all of those saccades that were between lines and within lines, and threw away the within lines one. So within line saccade is moving from something like that word to that word, whereas a between lines one would be moving from that word up to that word. And then we classified all of the between line saccades by their distance. And we found this. And I want to again emphasise these were really simple proofs. But nevertheless, the mathematicians in this study made substantially more between lines of K's of distance 1. And neither group made substantially longer saccades than that. That's probably just noise, and you expect a lot of random eye movements because they're quite hard to control. And when you do the stats, you find that there's a difference there, and that's all driven by that, not that. So the mathematicians are making 50% more between lines of K's of distance 1 than the students. Why are they doing that? So what we thought was, okay, we know that mathematicians seem to spend more time looking at text than students. We know that they seem to spend more time moving between lines than students. Maybe what's going on here is that they're doing this because they're searching for what the argumentation literature calls implicit warrants, which essentially is just a justification that's not written down in a proof. Because as you all know, if you wrote down absolutely every justification in a proof, it would be impossibly long. And you would be some kind of theorem prover, automatic theorem prover, or what have you. So normal proofs don't contain every justification or warrant, but nevertheless, if you want to validate a proof, you do have to work out whether each line is warranted or not. So what we did to investigate this is we took one of the longer proofs, and we did the following. So we classified each line-to-line transition as requiring a warrant or not requiring a warrant. And I'll say what I mean by that in a second. We then counted all line movements of the form from line n to line n minus 1, and then back to line n. So if you spend some time on a line, then you move back to the line before, and then you move back to the same line. Now the reason we did this is we thought this would be a sequence of eye movements that would be the kind of eye movements you'd probably be making if you were trying to work out what justified line n. So you think, oh, okay, I don't understand what's going on there. Let's look at the line above again and then move back. Now it's not the only eye movement that can do that kind of task, but it's one of the main ones. So here's a proof again, the same one we've looked at before. So this line here is interesting. This line here says, define a number A as follows, and then it defines some number. Now that line doesn't need a warrant, right? That's just defining a new object. You can do that whenever you want. You can just throw in a new object in the middle of a proof with cause no problems. You might want to motivate it, but you don't need to warrant it. There's no logical justification required for that. Whereas this line, note that dividing A by 4 leaves a remainder 1, does require a warrant, and it's not in the proof. So if you're validating that proof, you need to work out if this step is valid by doing some thinking. So we would expect there to be more warrant-seeking moves that start on this line than on that line. So was that the case? Yes, massively so in the case of the mathematicians. So you can see here that there's a really big difference between the kind of these warrant-seeking moves on lines which need a warrant compared to the ones that don't. But interestingly, the students also have a difference. It's just not nearly as big. Okay? And again, when you do the stats, that interaction is significant. So that difference is significantly bigger than that difference. Okay. So another way of looking at this proof is this diagram, which shows how the two groups move their attention around the proof. So the arrowheads here give an indication of the number of line-to-line transitions. What's kind of interesting is the two groups move their attention around this proof in basically the same way. So the only arrow that is in one group but not the other is this one, and that's a small arrow. But you can see in almost every case, the size of the arrowheads are much, much bigger in the mathematicians group than in the students group. And very notably here, but also here, and most other lines too. So there does seem to be something quite different about how mathematicians move their attention around proofs. And here's a picture, a video that shows this. So think about this video in comparison to how the standard written English was read earlier. This is the same person as the earlier video, I should say. So you can see they're really not making much progress at all in the way that you do when reading standard English. There's a lot of between-line movements of the type you just don't see when reading normal English. Okay, so what's going on here? Well, there's two possibilities, I think, each of which requires a different educational intervention. So one possibility is that undergraduates are just not very good at knowing when they have to look for an implicit warrant. Another possibility is perhaps they do know that how to do, when they should be doing it, but they just don't put enough effort into doing it, so they don't do as much of it as we would like. So we concluded that 2 is probably what's going on here because of this difference. So there is a difference between the warrant requiring lines and the non-warrant requiring lines in the undergraduate group. So they do seem to be doing something different when they should be. They're just not doing nearly enough of it. So this kind of raises this question, okay, what do you do about it? So if you think that students are capable of doing something, but they're just not doing enough of it to be effective, maybe you can just tell them to do more of it. So this was our pedagogical intervention. Just tell them, right? Just say, no, spend a bit more effort looking for these logical relationships. And does that work? So, can we improve student reading by telling them to do more of what they already do more of, but just not to the extent we would like? So this was my PhD student Mark, who spent time investigating this question. And what we did is we used a technique from the general educational psychology literature called self-explanation training. And the training we used was adapted from, in particular, Sharon Ainsworth's work in the context of reading school science textbooks. What does it contain? So, in the first 2 studies I'll tell you about, it used some on-screen slides that did the following thing. Well, firstly, it asserted that students should do this because it was effective. There's a bit of a lie in study 1, we haven't worked that out yet, but hoped it would be true. And then it said what you should do is every time you're reading a line in a proof, you should be identifying the key ideas in that line. You have to explain that line to yourself in terms of previous ideas you've identified in the proof, or previous knowledge you have from your general mathematical knowledge, which is essentially just telling students to search for these implicit warrants. So explain each line to yourself. It demonstrated what an effective self-explanation would look like for an example proof. And importantly, it distinguished self-explanation from what we call monitoring and paraphrasing. I'll give some examples of what that means in a second. So, if you just tell students to do more of this, do they get better at reading proofs? So one of the Mark studies was a lab-based study with 76 undergraduates, randomly split into 2 groups. We asked them to read a proof, and then gave them a comprehension test based on that framework I talked about earlier. And they could get a possible 28 on that test. So this was the design. So we randomised them into 2 groups. Some of them got this training, some of them got some kind of control activity, some history reading about triangles or something. Then we got them to read a proof, and then this is important. Then we asked them to explain the proof line by line, in this group using their training, and in this group just explain it please. And then we gave them a formal comprehension test. So we were hoping that this training would lead to better explanations here and higher comprehension here. So we used the Think Aloud protocol there, and then coded what they said according to explanation types. So these are the explanation types we coded for. So we split up explanations into 3 types. So principle-based, which is an explanation based on definitions, theorems, or ideas not explicitly written in the proof, so prior knowledge. a type we call noticing coherence, so some kind of, we're doing this because of what happened in line 5 or whatever. So those two types are what I would call a warrant seeking earlier. There was also a type called kind of goal-driven, which was relating to high-level structure. We're trying to derive a contradiction or whatever, so we're going to do this. Which is also an explanation, but it's not a warrant-seeking explanation of the type I was talking about. And then we also coded in non-explanations. So sometimes students, of course, don't say anything or say something wrong. Sometimes they paraphrase. Now, it's really important. So the training materials did say don't paraphrase. Paraphrasing is just repeating what the text says, but rephrasing it. And that doesn't require you to bring in your prior knowledge or link it with other things. So that's a bad thing to do. Well, bad thing to do, but it's not going to help you learn in the same way. And neither is monitoring. So monitoring is saying something like, yeah, I understand what's happening here, or this is a bit confusing, or whatever. They are not explanations. So we were hoping to get more of those in the self-explanation group. And indeed that's what we found. So these were the ones we wanted there to be more of in the self-explanation group, and that's what we found in every case. And we found less monitoring in the self-explanation group than the control group, but not less paraphrasing, interestingly, even though we told them not to do that. But it's not a bad thing to do that, as long as it doesn't stop you doing the good things. So that was good. So this was a true experiment. Participants were randomly allocated into groups, so we can say that there's a causal relationship between our training and producing better types of explanations. So would that lead to better comprehension? Yes, turns out to be the answer. So because this was a lab study, we included the time they spent reading and the covariance analysis. Doesn't actually make much difference, but when you study, here's the means of our score out of 28. So the self-explanation group got 18 out of 28, and the control group got 14. And that's a really big difference. That's a 1 standard deviation difference, which if you believe effect sizes are interpretable, you would be impressed by. But you probably shouldn't. Anyway, let's not get into that. The other interesting thing about this result is it transpires that this training seemed to be more effective the more background knowledge you had. So the further you had got through your degree course, the more effective the training materials were, which is exactly what you'd predict, because if you've got more knowledge and resources to draw upon to construct your explanations, we would expect you to produce better explanations. Okay, so this was kind of exciting. Self-explanation training leads to higher quality explanations and to better proof comprehension, but it's a kind of a weird lab study we've done there. So we had forced them to explain in that stage of that experiment because we wanted to record what they said. Does our self-explanation training change reading behaviour when we don't force them to explain? So it'd be nice if our students, having done the training, made eye movements more like the mathematicians in the study I told you about earlier. So that's what we tested. So we got 32 undergraduates to do this rather complicated design. It's not as complicated as it looks. So we randomly split the participants into 2 groups, one group that got the training and one group that didn't. And each group read a proof before they did the training and read a different proof afterwards, and those were counterbalanced between 2 different groups within each group, because sometimes the proof makes a difference. Well, always the proof makes a difference in how you read, of course. So each person read a proof, had some training or a control activity, read another proof, and after every time they read a proof, they got a comprehension test. So, what can we conclude from that study? Well, we looked at 2 things, well, we looked at lots of things, but 2 things I'm going to tell you about. Cognitive effort. Is it the case that self-explanation training increased cognitive effort? That would be nice. And do they do more of this moving attention between lines in the way that seems to be associated with effective proofreading? So, cognitive effort, yeah, there was a really big difference. This was the mean fixation durations in milliseconds of the 2 groups, and you can see the self-explanation group had, what's that, 15 milliseconds longer clean fixations on average, which is the kind of difference you'd associate with with more complex processing. And that's what we were hoping was going to happen, of course. Good. And the same kind of positive result with logical relationships. So these are the total number of between-line transitions made by the two groups. And you can see I've split it by proof there because it turned out one of the proofs was quite a lot more complicated than the other one. But there was a significant difference between our two groups. So in both cases, both proofs, the self-explanation group did more of this moving attention than the control group. And this just tells you need to be a bit careful when choosing proofs in these kind of research techniques, because not totally unsurprisingly, proof, how you read depends on what you're reading. Would be peculiar if that wasn't the case. Okay, and no significant expression. Okay, so that's handy. Self-explanation training seems to, which I'll just remind you is a really simple intervention, it takes 10 minutes or so, just tells students to do more of what they already know how to do, seems to lead to increased cognitive effort and more attention to logical relationships in proofs. But that was a lab study too, of course, because it was an eye movement study. Here's a question. What if you do this in a genuine pedagogical setting? So, can we move from the lab into a classroom? So, we tried an intervention in our first year analysis course, which actually should have had quite a lot more than that, but that's how many people turned up. And we randomly split them into two groups based on the parity of their student number. So this was done in a lecture in a very authentic way. And then we had this design. So what do we do? We split them into two groups randomly. One group read some self-explanation training. Another group had some control activity about general effective study habits. They all read the same proof, and then they all did the same proof comprehension test. And then, nearly 3 weeks later, they read a different proof, did a different comprehension test, and then got the reverse activity, which was the ethics people claims we had to give everything to everyone. But we didn't do any missions after that. Okay, so what are we hoping here? Well, we're hoping that if our self-explanation training is effective in a real situation, we would expect certainly higher comprehension test scores here. It would be really nice if we got higher comprehension test scores here too. That would tell us that the effect lasts for at least 3 weeks. And, somewhat to my surprise, that is in fact what we found. So I was really expecting that difference, but I was expecting that to be much smaller. So in the immediate post-test, our self-explanation group did better than our control group, and more or less identical results 3 weeks later. And again, when you do the stats, that's everything that looks like it's significant there is. Okay. So one interesting thing here, and this is true of research in general, is you'll recall that I told you in the lab study, this intervention improves scores by 1 standard deviation. So when you move into the real world, sadly everything gets worse. So it only improves scores by 0.4 of a standard deviation, and that's typical, unfortunately, because the real world is much more messy than nice, clean labs. But still, that's not to be sniffed at. Improving reading scores by between over a third of a standard deviation is quite good, I think. So the question, does self-explanation training work in a genuine pedagogical setting? The answer to that seems to be yes, and the effect seems to last longer than I was expecting, although the effect is smaller than you find in a lab. Okay, so let's reflect a bit about this. Why is this a good thing to do, and how does it differ from our e-proofs? Well, self-explanation training forces students to do hard work, right? It forces students to do this effortful linking what they're reading to their prior knowledge. forces is too strong, but it encourages students to do this kind of hard work, cognitively difficult work, and that's reflected in their eye movements. Whereas the e-proofs were really just too easy. It made it really easy to outsource all of that hard explanatory work to the recorded explanations. So you kind of didn't have to. You didn't have to do much thinking when studying the e-proofs. And indeed, Shamali did a series of studies which kind of directly showed that, to do with when people clicked on the audio, the level of their engagement with the proof went down quite dramatically. So this is kind of an encouraging result for several reasons. Mostly, I think this. So a lot of education research is of the form, students can't do this. You know, students can't do something. Which is important to know, but this is a different kind of result. This is of the result that students actually do have all of the relevant skills. All you've got to do is just push them in the right direction, and then they can really make quite a significant change to the activity they're doing and the effectiveness of the learning that results from that activity. So I think that's quite a nice way of thinking about this. Our students can actually do more, sometimes more than we think. Just need a bit of a push in the right direction. I'll say a few things more about methods as well. So I think the thing we learned from the eProof study is a really nice, clear example of the following: that students are not very good at reporting on the effectiveness of their own learning. And again, there's an awful lot of educational research that demonstrates that. I think another thing it tells us is that colleagues are not very good at correctly reporting on the effectiveness of their teaching. So it's not true to say, or anyone else is teaching, right? Observing teaching is a very unreliable way of assessing teaching quality, if by teaching quality you mean learning outcomes. And this is a real worry, because this is essentially all we do in higher education, in the vast majority of cases, is ask students to fill in feedback forms and do sort of, well, at least in my university, if you want to pass, a new lecturer wants to pass probation, they have to be observed by someone. And if they fail that observation, then that's a serious problem for them. But I think this tells us that we shouldn't take those sorts of measurements too seriously. If you want to know whether someone's learned something, you've got to test for it, unfortunately. Okay, so some practical consequences of this. These self-explanation training materials are now included in some textbooks. So this was quite exciting, because this was the first ever textbook I bought as an undergraduate. And in the second edition it includes these materials, which is quite good fun. If you're interested in using these, then please feel free to download a tech file from that website and do what you will with it. Or you can download a glossy brochure that we got the university to pay for, which is probably less useful for you, but it has some pictures in it. Thank you very much. Stop there.
Right, there's not much time, but we can take a few questions. Any questions? Everyone?
So you needed people to evaluate what the students were doing, right? To judge whether this was sort of this, which kind of, like when you gave them a score, it was people giving them a score, right?
In the comprehension tests? Yeah. No, well, in some sense I suppose, but no, it was multiple choice questions. So it was a written exam, so the Rutgers work ends up with a series of multiple choice questions of different types, which assess different dimensions of proof. Yeah. But we did in the third study, the one where we asked them to give explanations and we recorded them and coded them, then that was a judgment score, but we did an inter-rater reliability to check that people were judging it in the same way.
And was that one done double blind?
Yeah, I think so. So, well, depends what you mean by that.
Did they know, did people know which people had done the self-evaluation thing? Or that was a different study?
No, that was that study. I couldn't believe it some years ago, I'm not sure, but I don't think it would make much difference, because if you're doing the coding separately, then it's the inter-rater reliability. It could, if people weren't judging the same thing, even if they knew which group they would come from, unless they were systematically evaluating. So I don't think that would affect the iterative reliability much. It's my intuition, but yeah.
Any other questions?
Did the students feel like they had understood the proofs better? Like, did you talk to them? Did they feel they had a deeper understanding?
From the e-proofs or the...
No, not the e-proofs.
From the self-explanation?
Yeah.
So students, people react quite... So I think this is really interesting, right? So the people are not very good at knowing how much they've understood. They are pretty good at knowing how much effort they've had to put into understanding it, right? So if you feel like you've put a lot of effort into trying to do something, that's bad, right? That suggests to you that this is really hard, you've really struggled here, bad. But actually that's really the most effective way of learning things sometimes. If you're struggling with the correct, the educationally valuable activity, that's good. So I kind of don't really put much...
I know, I just was, I agree it's not a good measure,
Yeah.
but I just was interested in if it made them, I don't know if it had any effect on sort of how they felt about things, because if it has a positive effect on how they feel about it, then that's also a good...
That's true. I mean, one thing I would say is the material has a large section about how effective it is. Right? I think that's an important part of it. So if they've read it properly, they ought to believe me that it's effective, right? And I think if you don't include that, then you really do get into these problems of you're just making this harder for me and I'm not getting anything out of it. So I'm not, yeah. So, no, it's an interesting point. We didn't do any kind of focus
I was
groups.
just wondering if you had any anecdotal, chats with students or anything like that.
Did you ask them any questions as to why they decided to study mathematics as a major? What their motivation was? Whether they become an engineer, or a physicist, or interest in mathematics, or what?
No, not in this study. I mean, so these were all single honours students at Loughborough, who, I mean, to be honest with you, the vast majority of our students have chosen it because they did well in school, and sort of that's their only...
Yeah, that doesn't surprise me, but I thought if you read some harder evidence than more recent.
No, not from this study, no.
I just wondered, when you carried out your original e-proofs, why do you set such nice flattering comments for people to indicate their acceptance of things? Why don't you give people much more negative comments, which they might actually respond to in a very different way?
So we did actually. So of the eight statements, 4 of them were negatively coded. So 4 of them of the sort, no, I found it a waste of time or whatever. And then you flip the scores.
So you showed us the nice positive one.
Yeah, I didn't want to confuse you. Yeah. But no, that's right. No, for exactly, I imagine the reason you're asking that, yeah, it's the best practice to have half of them coded one way and half the other. So you don't just get enthusiastic people being confused.
So when we study the differences between novices and experts, right? So the approach that you took was to give them the same thing to work on, right?
Yeah.
But alternative could be is let's give different stuff that are challenging to both groups.
Yeah.
So could you reflect please on the decision not to go in this direction?
Yeah, so that we got criticised by that actually. So the people who claimed, so there was this, as I mentioned, there was this issue. Some people, in fact, so the Rutgers group did a lot of interviews with mathematicians, some of whom claim that the best way of reading a proof is to skim read it really quickly, so you get a sense of the overall structure, and then only then read it line by line. We didn't find any evidence of that whatsoever in this paper, and quite rightly they said, well, that's because these are really simple proofs, and that could have been true. So we did actually do several follow-up studies to investigate that. One of which was quite a good fun study where I got a load of my colleagues to send me a paper they wanted to read but hadn't yet read. And then I got them to read it on an eye tracker. And this was a paper, not proof, so it might be slightly different. And the interesting thing we were interested in is do they do that kind of skimming of the paper when it's a genuine research level article, they're actually reading for their own work. And no, they don't, it turns out, although some of them thought they did. And I think probably what's going on there is, you know, a well-written paper kind of does that, all of that work for you. You know, structures, tells you where you are in the paper, what's going on, where you're going to go next. So I think, again, this is a good reason not to trust people, really. A lot of the kind of work, a lot of cognitive work is not reportable reliably. So yeah, we have done some of that. But I think there's something, I mean, one of the graphs I showed you showed that proofs, that the type of thing you're reading really makes quite a big difference in how you read it, obviously. So I think it would be pretty hard to interpret a between groups comparison if they're doing quite different things. Yeah.
Wonderful, I think.
Did you actually do any eye movement training, or did you simply just get into it slowly?
Eye movement training?
You know, like getting them so that their eyes moved, you know?
Oh yeah, so
exercises, sorry.
Well, I mean, so yeah, if you've ever done an eye movement experiment, in order for the tracker to know what's going on, you have to do what's called a calibration, where, so it happens, essentially a little dot appears here, and I say, can you look at that, and it goes, vroom, and then, you know. So you have to calibrate, because everyone has slightly different eyes, and you know, so it's slightly further away and closer or whatever. So there is a calibration exercise before you start any of those kind of recordings.
But not like in the training of interpreting material, like the way the eyes track. So you follow how the eyes track, but there's obviously an optimum way, almost, for eyes to track.
So you mean, how do they read the self-explanation training materials? No, we've not done that. I mean, they're pretty standard English, so I wouldn't imagine there'd be too many differences in how people read. But yeah, it's interesting. Yeah, no, we didn't do that. It's an interesting question.
Right, I think there will be an opportunity to ask more questions. Upstairs, level 4 commons area, with plenty of refreshments. Matthew will be there for hours, so please come. Let's thank Matthew.